Thanks everyone for coming. My name is Wallace. I'm going to talk about research on adaptive augmented reality workspaces. So if we look at how AR systems have evolved like in the last 50 years, we see that how technology has been making these things more wearable and portable, like lighter. And we're already reaching the point where we have something like a regular glass that we can just stick in our pockets, right? And maybe even wear it the whole day, right? Like I do. And the question becomes what we are going to do with this device, with all this technology. Well, first thing is we're going to chase Pokemons around, right? Because that's so much fun, right? And this is a type of application where the content will just becomes part of the environment. But we also be doing something else, like writing papers for UI and looking at our schedule, right? And looking at web pages. And the point that will happen is that we use the AR devices to just replace all the displays we have in the world, right? So the monitors, the displays we have in our pockets, right? And this brings some interesting questions for interface design. You need to think that it's something like being able to carry your multi-monitor setup anywhere you go, right? So imagine you're in home and you have all the interface laid out, right? You don't have windows anymore, so you can have like all your workspace around you, and then you decide to go somewhere else. What should happen? Should we take those windows with you? You should like adjust them and carry them manually. You see that easily become very impractical to do, right? And what also happens if you decide to actually walk around with this, right? Some people go from one place to another and check their schedule while they're on the way, right? And this also adds another challenge because you need to deal with the interface while you're actually trying to navigate the world. And our solution for this thing was, what if you could think about interface that could adapt to the things that you do, know when you start walking, and it is able to understand the environment around you and adapt so that it's always out of the way, right? So to give you an idea of how this would work before we go into more details, I'll show a little clip of how this actually works, right? So now the windows are on the wall, and then the person decides, oh, okay, I'm going somewhere else, so they can detach from the wall and follow you around and react as you change your trajectory from one place to another place. Right? So the methodology we used was first make an analysis of the design space, right? What are the different ways that we can do this? Right? And then we followed by design and implementation, or actual implementation in AR, and followed that by a contextual user study. So our point of start was the framework from Brusilov et al., which tried to come up with a structured way to understand how to build adaptive interfaces. And what we did in this case was to also consider the context, right? So instead of just looking at what the user is doing, we want to use what is happening, to look at what is happening around you, right? How the environment is changing as well. So we have information from the user environment, what the user is doing, the information about the environment, information about layout, so we know how things are being displayed in the environment. And the point here is that besides being able to look into explicit commands like gestures and button clicks, right, we also have information about the user, where the user is looking and if it's moving or not. Right? So to give an example how this could work, think about like using body position and body orientation as features for adaptation. Right? So we could build an interface that knows that you start walking and follow you around, and knows when you turn, and is able to keep the same relative position to your head, right? But you can also instead of looking at the body orientation, you can also look at surface positions and surface orientation around you, right? So you can build an interface that as you walk around down this corridor, for example, it follows you, but not in front of you, but rather on the wall, so that don't block your way. So what we did was to implement like 18 different behaviors, like scattered along all this design space. And we look into this like user information we get from the user, from the environment, from the layout, and also from combination of this. So you can think, for example, have an adaptation to like the wall, to the environment, but only make that happen when you get close enough to the wall. And to be able to run this with an actual user study, we reduced this to the 4 more promising behaviors, and I'm going to show each of them now. So the first one is adaptation to position. So basically, as the user walks around, the interface can adapt and follow you around, but it ignores any kind of rotation from the head or from the body. The second one is the rotation behavior. So in this behavior, come on, we ignore the position, but we react to any changes in rotation for the head or body. The third one is adaptation to the environmental surface. So basically, you move the interface elements to the walls and interpolate both like position and orientation. And the last one we call auto-centering. So this is a combined behavior where it works like as follows, but it adapts to your change in trajectory as you walk around. So with auto-centering, you can look around while you're walking because it's not attached to your head, but when you change the trajectory, it also adapts to that change in trajectory. And we also build an interface that allows participants to choose from all these 4 behaviors whether they wanted it on all the time, off all the time, or they can also choose to assign each behavior to a button so that they can would be activated only when you press the button. So this gives the participants chance to activate on when it makes sense to them. So we ran a study with like 14 participants, and our goal was to identify the strengths and limitations of this type of adaptation and investigate how participants could use this system in real setting, right? And another goal was to generate like new ideas and directions for this kind of spatial adaptation research. And we ran the study in 2 scenarios. So in the first scenario, it was a work scenario. The participant would pretend to be an interior designer, right? So, and the experimenter would be the client. So they would walk around and trying to discuss things about like renovating an apartment. And the second one was a vacation scenario. So 2 of them would pretend to be friends and talk about things in daily life. Oh, what are the news? And can we go to the beach at one day or not? So this is the layout of the actual environment we tried. For the first one, which is the work scenario, it was an inside environment with a lot of obstacles and tables and chairs. And for the vacation scenario, we did it in a corridor, long corridor with a bend in the end. So in the first scenario, it was important to note that there's a task in the end that required the users to interact with items in the real world. So we asked them to draw in an actual board with an actual marker. So for the first scenario, the work scenario, the participant had like 3 windows available to complete the tasks. One had like notes about what was decided in the prior meetings, a list of furniture and prices, and also a floor plan. So the experimenter would ask questions like, oh, what we decide about doing in the kitchen? And, oh, where does expensive furniture that costs $1,000 will actually go? And the participant would then need to check all these windows and be able to answer while walking around in the space. In the second one, as I said, was like 2 friends talking to each other. So for this one, the interface used was a weather forecast, a calendar, and also a web page with news. So in this case, the talk was more about, oh, do you know what is happening in science recently? And do you think we can go to the beach on Thursday? So we need to coordinate and check information from all these windows while walking and talking. The measures we used was basically observations and semi-structured interviews, and we also record the log for participant interaction so we could review it later and see where the winds are going and where the person is looking and what combination of behavior the person is using at one specific moment. So going to the results, when you look at the combinations of behaviors used, the 2 most used combinations were follow on and auto-centering on, and the second one was follow on and rotation on a button. So let me explain what that means. So in the first one, the window would follow automatically the user, right, and adapt to any change in trajectory. In the second one, they would follow the user but not adapt to any change in rotation. So to be able to actually make the window move back to the original position, they needed to press a button. We also did a dimensional analysis to try to figure out, oh, what are the main characteristics that are desired for this sort of adaptive interfaces? The first one has to do with a trade-off between usability and expressiveness. So basically, participants preferred when behavior was useful in multiple situations, in multiple contexts, and it was stable and easy to use. The second one has to do with the compatibility between vision-body coordination involved in walking So when you're walking, you try to look around and see where you want to go and looking for obstacles, right? So interfaces that require you to look in a place that you would not actually be looking were not that desirable, as well as interfaces that actually occlude and block the view. And the third one has to do with the compatibility with like real-world activities. For example, in that last task that I required users to draw something on the wall, they need to be able to look and see the other face and look and see, oh, where the marker is, and then be able to look at the board and see what they're doing actually in the board, right? So this has to do with not only be able to see things, but be able to position the interface at places in the world that we actually want them to be, right? Another thing that we did was an analysis of how the behaviors were actually used, right? Because one thing is, as we as designers try to, oh, I think it will be used in this way, but we're also interested to see how novel and different uses people would make from these behaviors. So we found out like 4 main ways that they use this interface. The first one was to organize information. So even though each behavior, each scenario only required participants to look at 3 windows, all the windows were there the whole time. So participants would use, for example, attraction to the walls to organize information. Oh, okay, that's where the information that I need. That's the calendar, where the calendar is. Another reason was to obtain information. So sometimes when you walk and you want to quickly check your calendar, they would like press the button and bring the interface over here, check the calendar, and then dismiss it. Right? Another one was to compensate for lack of awareness about what is going around when you're walking. Right? So attraction was one of the behaviors what was used for that matter, because it can just clear the space around you, sending all the windows to where there is actually natural occlusion in the world. And the third one was to harmonize AR with the world, right? So we never see, for example, things that are half inside the table or half inside the walls, right? So participants also use these different behaviors to make things being coherent to the way they expect the world to function. So in summary, we found out that these adaptive behaviors can be effective to support AR and walking. And the behaviors we designed end up being kind of easy to use and easy to understand. But this final behaviors only represents like a minimal useful set of abilities and things that you want to have in a real actual interface. That's it. Thank you very much for your attention.
Hi. So I was curious about, in your studies, did you find any correlation between the density of the layout and the behavior that the user adopted? Because I see a lot of behavioral things that you discussed, but if you have a lot of priority content, but how much content you have, and did that affect whether they choose it to follow or rotate or things like that? So.
Mm-hmm. Yeah, that's an interesting question. Thanks. So one of the things that in the beginning of each scenario, we asked participants to lay out the interface in the way they wanted, so they could just look and drag them around before doing the actual task. So then you see that, for example, the limited field of view of the HoloLens might have influenced them to adopt specific layouts, right? So if they knew that, oh, I will want all this information in the next task, they would put them together, right? And then they would find out, oh, they're too close, and I'm going to have them blocking my environment. So certainly we saw a lot of just relationships between the field of view, right? The amount of windows that we actually have and we required for the task. So we have just 3 windows which were the ones that were actually required. The other ones were not. So some people would just drag the other windows that they know wouldn't be used very far away so that they could have the environment more clear for walking.
Hello? Nice presentation. I was wondering when they were dealing with the physical world and the virtual one,
Mm-hmm.
and they had some kind of obstacle, so if they were going to crash into something because of a screen in front, would they rather adjust the virtual things and make a rotation or the attraction feature so that everything goes away from the field of view, or would they adjust themselves physically and move back, or just reorient themselves?
Mm-hmm. Yeah, we
Like,
observed
so-
a couple of interesting solutions to, especially dealing with things in the world, right? So for this last task that we required people to mark the position of the furniture on the actual board. Some people, for example, use the traction to make the virtual map align with the real map on the board, so they could just look like this and mark, right? Some people prefer to put it on the side, so they have a clear view of the board, and we just check like this and mark it there. Right? And regarding interaction with other things in the space, for example, when you're walking and you see, oh, there's a chair here, right? And I want to go over there. They will actually stop or reduce the speed so they could actually see through the windows. But most of the things we noticed regarding doing the task and walking around was more related to lack of attention than actually because of real occlusion from the AR windows. Thank you.
Okay. So, if there is no other question,